to get it to do so. And half the bugs were my coercion model, and half the bugs weren't.
You mean it's not just a proposal, there's actually working code for it?
Oh, you're using it right now. It's already in Sage.
Okay.
Yeah.
Cool.
That's why this is called the coercion model. It's coercing. Robert, what are you up to?
Yeah. It's not so much a proposal anymore.
Well, there is a proposal part, because it's not supposed to propose.
Well, there was a subtitle in the abstract. Like,
He just wants to increase the chances of acceptance.
Yeah.
By just shoving it down the throat.
Okay. So there's kind of two pieces to this. There's the mathematics piece, which I think is the controversial part. There's a mechanics piece, which has some unanswered questions as well. So in Sage Days 4, we came up with this big list of examples of things that should happen. We mostly agreed by the end of what the right thing was. So for instance, Z, if you have a polynomial in Z and you divide by Z, you don't want to get a fraction field. You want to get rationals, polynomial with the rationals. When you add things like this, it should automatically do the right thing. Same with this, it should be an error, because we don't necessarily have a coercion from the rationals to the integers mod 5.
well, okay, no.
Well, okay, yeah. The thing is,
Oh no.
with coercion, yeah, this is one of the design decisions. It should always work or always fail. You don't want to work on some things, not on other things. You don't want to say, well, this will work as long as your element here doesn't have any 5 in the denominator. This will fail due to an error in you don't know the relationship between x and y. Do they commute? Do they not commute? If so, which one comes first? Which one comes first is important in Sage for calling conventions, for instance. Even though, of course, they're equivalent. Something like this, we decided should work. And that's because cyclotomic fields, when you create a cyclotomic field, when you create a number field, if you pass a cyclotomic polynomial, it will just be an abstract number field. But if you actually call a cyclotomic field, you can create them, and they're created with a standard embedding into the complex numbers in the Q-bar, such that you can figure out, make sense of something like this.
That doesn't even matter. Even abstractly, that makes perfect sense, because you just map the generator to the right generator, and it's all okay. So it's nothing to do with Q-bar, I reckon.
Well, if
nothing to do with
if
C.
M and N are not coplant,
Then there's a choice.
then there's a choice.
Yeah.
Yeah.
Yes, that's true.
Yeah. Otherwise,
Sorry.
well, it's the same.
Otherwise, finite fields would be easier.
As long as, yeah, with number fields, if you add two number fields whose intersection is Q, you can do it anyway. It's just a question of you have to use this embedding information if there's some non-trivial intersection. Finite fields should be able to work. And something like this is a little bit edgier. But the really edgy case is what about Z mod 5 and Z mod 3? And you get the 0 ring and yeah.
I don't know, like when I see that last one, and then I look back at Q times Z mod 5Z, it just feels like it should just be going to the trivial ring or something.
Like this one should be going to the trivial ring?
No, that one, the one you just played. Oh. Should just go to the ring with just a 0 element or something.
Because they both go to the ring.
I don't know, that's just, if you're going to do that at the bottom, it feels like a tensor product over Z. Yeah. It would be the 0 ring.
So and there's also the idea, though, that this has not been implemented. This stuff like this would work, but the 0 ring would, by default, throw an error when it was created. So you could create a 0 ring, but you'd have to explicitly say, yes, I do want the 0 ring. So but if it's ever created in the process of doing coercion, it would just throw an error and say, everything from here on out is trivial, which is probably not what you want. So.
Well, you're just saying it's 0 mod 1.
Yeah.
So if you add
the answer is
apples
0
and
mod 1.
oranges, you get an empty system.
Yeah.
And that now you can actually invert.
I mean, the issue though is there's never.
But the thing is, the error tells you all the information you would ever get out of it.
So going back to the cyclotomic one, I still don't understand it. So if I take if I take m equals 3 and n equals 5 or something, so I embed these in Q of zeta 15, and It's just that the cube of zeta 15 gets mapped to is the
Yeah.
same as what the generator of this. So why do you need embeddings? I don't know.
It's when they're not
3 and
co-prime.
5 are coprime.
So when they're not coprime, but that's okay too because yeah. That's the case. I thought
What
it was
is
okay.
zeta 15 to you? Is it a root of some polynomial or is it?
It's the
complex
generator.
number?
It's the generator x of your number field. So I mean,
Why couldn't you do exactly what you're saying with finite fields?
because there you don't have a canonical choice of minimal polynomial, whereas for the cyclotomic ones you do.
It's the primitive roots that you have to take a difference to.
Yeah, I think if these are not co-prime, then
Yeah.
depending on the choice of
Yeah.
primitive roots, the relationship
Yeah.
between these guys will change.
I'm saying the primitive root is x in all cases,
Well, the primitive root here is x, the primitive root y is,
Yeah.
here is y.
right?
But the
And so the-
relationship between x and y in this ring will be different depending on your embeddings.
Depending on the way you embed, say, q of zeta m in q of that other guy,
Yeah.
and the guy on the right. But I'm saying that you can build a consistent tower of them.
Yeah.
Yeah.
But you have to do so.
And that's
But-
what you're doing.
But there aren't any choices, so
Yeah, this,
And
well, you could make a canonical choice.
Yeah, that's what I'm
of
saying.
You always choose this.
so,
Like-
Okay, you're saying the same thing.
isn't
Are we
the
saying the
fact,
same
the
thing?
fact that you can make a canonical consistent choice is equivalent to the fact that you can embed all
Yeah.
you have canonical embeddings into a common field.
yes.
So
So you're choosing your
Yeah,
roots of
but
unity before.
sorry. The only thing I had any objection to is you were talking about complex numbers before, and I don't see where that comes into it.
Well, you're embedding it in the cube box.
That's just what he came out of his mouth before.
Yeah.
But maybe
That's how I
okay.
think.
Okay. Sorry.
Okay. So.
Look, you're just wrong. Okay, I just got to say this because you wanted argumentation. So
So then there's this example here that's a little bit more complicated, but it should work. So we have rationals, matrix over
Yeah.
polynomial ring should give you.
Can you
Wait,
a
wait,
scalar to a matrix?
Yeah, with n equal to
We
m.
would make
Yep.
this into, this is, oh, this should be an M.
Okay.
I mean, and it becomes a
Yeah,
diagonal.
square matrix makes it,
just
Yeah.
change it by multiplication.
Yeah, as long as that's a square matrix.
yeah.
Yes.
Or for instance, you should be able to multiply here.
Yeah.
Yeah.
Yeah,
Yeah.
I'm not sure I want to be able to add, but I certainly want to be able to multiply.
Like
Adding is nice.
a plus 1. Or is
Yeah,
it
I think I'd rather get an error message if I do
Yeah.
that.
why?
Because I'm more likely to do it by mistake than on purpose.
I guess, I
But
mean,
it's
the
like,
Bowman
if you look at a
equation does
paper,
A minus 1.
it's extremely
So you
unusual to
create
not
an
see that in
identity
papers.
matrix and then, but,
Well, in one
That's
case
true.
you're talking about rings, and in another case you're talking about non-rings, right?
but a square matrix is a ring.
Yeah.
Yeah, I mean, it makes,
Yeah.
it makes perfect sense,
Yeah.
but.
Oh, so when you
I
multiply
still
by a
think from
scalar,
point
you
of
don't do
programming,
that
we're more
coercion.
likely to make that, say that.
That's a scalar
It's a
multiplication.
scalar multiplying, yes.
Now, is that a scalar multiply when you're multiplying q times a matrix?
Yeah.
Okay, so the matrix gets coerced and then you do a scalar multiply?
Yes.
No, that's what I mean, you don't need.
And that actually works out.
Yeah.
The multiplication by the coefficient will already change them to become a
So,
matrix. Because an implicit one without.
so for instance,
That's 1 times x plus 1.
question was,
There's it gonna be.
Can't take that part of it.
well,
Plus, obviously, the constant term. And you're supposed to constant.
Should we do it a different way?
Choose a random size. Maybe it should actually.
So long as they
Just between 0 and 2 to the
Guys, did you see
between 0
that?
and 2 to the
Did you see
10,000.
that?
so,
What?
there it is.
That's very cool.
Yeah.
What 1/2 plus m?
Okay,
So
you
that-
multiply it by a number field element?
No.
Oh, no.
No, that's great. Can you multiply by a number field element?
I object.
And then the,
No, because there's no embedding of ZX. Oh, maybe.
Yeah.
Yeah.
Z
Ooh.
should go in anyway.
I like that.
so,
Well, sure, a lot of 3s in the same.
Yeah, it just commutes all the way down to the bottom
Yeah.
somehow. Can you
That's
multiply by an element of z mod 5?
This guy you can.
Yeah.
Hmm?
Yeah. Can you multiply by some like random number field element?
Yeah.
Square root of minus 1 or something?
Well, square root of minus 1 is currently a symbolic ring element, which will work, but
Yeah, do that.
that took a long time because I had to start with the maximum process.
And simplify the answer. In order to simplify the output.
Yeah. So,
Can you
Yeah, is that
compute
a
the
chord?
exp of a matrix with that? Will it automatically start working with denominators?
whatever functions the matrix supports, you can do it. I think,
Yeah, so you can just plug it into a polynomial there.
yeah.
Oh, but x with
Yeah.
that doesn't make sense.
Oh,
Yeah.
yeah, but I mean, you
Yeah.
could take a
Sure.
translation to it.
You still didn't do a number field element.
So, yeah.
No,
this
I
is,
is good enough,
yeah,
isn't
this
it?
is-
Is this one?
Oh, no, that's
the
symbolic.
That's not a number
the
field element, yeah.
State of the symbolic stuff?
Oh, you have to
You
give
need
the
alpha.
yeah, give it a name. Wow. Amazing.
Okay, so if I now have a projective variety over Q,
If I have a mixed
is-
motive.
Yes, well, if you implemented it for your projective variety. So for instance, elliptic curves over base rings, I believe, work.
Really?
also with bad reduction.
What was the question?
There was
Is
a
it-
question.
Oh,
well,
The question like you can't
I cut it off there, I was talking about the same question.
No, I was going to
You
reduce
do something
mod
like,
P.
oh yeah, take an elliptic curve defined over like Q and then start creating points defined over number fields or something?
So like the idea is if I have an elliptic curve defined over Q, and I have the same elliptic curve defined over, say, Q adjoin square root of 2, and I add 2 points, that should be okay.
Great.
How does it know it's the same elliptic curve?
If it's not the same elliptic curve, it'll throw an error. Because it can't find a canonical group of both of them.
How do you know which isomorphism between the two?
Yeah.
It-
Well, in that
Right,
case, there's a
minus.
canonical one.
There's a canonical one of the rationals embedded into the field.
You mean assuming that the equations?
I mean, assuming they have the same
If-
equation.
If it's the same equation, it'll work. If it's not the same equation, then it won't.
Yeah.
It shouldn't.
But you could define a morphism between them.
I'm
Yeah.
not being completely facetious about the thing being off by a minus sign. I mean, if
Yeah.
these viruses, if you got these things not by actually physically typing them in,
Mhm.
but by sort of taking some taking some cubic and turning it into Weierstrass form.
Uh-huh.
And it just happened that you did 2 different cubics the same ways and you got the same equations. You wouldn't want them to be considered identical
I agree.
because you hadn't really specified that between them.
As a word of warning, I'm sure that your model will never do that. But in Magma, for instance, one should ask that 2 number fields were isomorphic. If you put an element in the one and then pulled it back, for a while it was the case that it could very well be that you got back minus that thing.
Yeah, so right now, 2 number fields can be isomorphic, but you won't be able to do arithmetic between them unless you establish the relationship. Yeah. So there's a couple of cases. The easy case is if you have the canonical coercion in one of the directions, and then you just can course that way. This is the case that was implemented already. The original case, I think from as far back as I looked in the course model.
Yeah, didn't it? Yeah.
So either they're the same, or this can go to there, or this can go to there canonically. Otherwise, you fail. And then we got a little bit more complicated with what about being able to multiply by element to the base ring? But the thing is, so you could do something like if x, like you take a polynomial of the integers times a half works, but a polynomial of the integers plus a half didn't work. So that's changed. Then the medium case is if there's an embedding that's specified. And we'll get to this later. This is the idea. Okay, that should maybe technically be Q bar, but where you have an embedding that allows you to instantly go from one to the other. It might not be canonical, but it's been specified by the user or by on creation time Or for instance, when you create a quotient object, this would be, it would already know about its embedding from the thing it came from.
Or is that?
Projection.
Well, projection, yeah. I guess embedding isn't quite
It's also
the specified morphism.
And section.
What was?
I mean, if you can.
And section's not going to really happen
from R to S and S to R,
by default,
how to choose?
because there's a choice involved there.
Is X
Yeah.
only one direction should be canonical.
No, you could have both maps.
So how do you choose it if both directions are
Okay.
canonical?
Yeah, so if both are canonical and there's no choice, if they're canonically isomorphic, then what you do is you just pick the one on the left. And it doesn't really matter because next time you do arithmetic, it doesn't matter which one you have because then you can go the other way.
As long as everyone has been following the rules.
Yeah. But the idea is it really doesn't matter which one you pick because it can go back and forth. So,
Except for execution speed.
if they're really canonically isomorphic.
Yeah.
Otherwise, if there's any difference, then you have to say, well, which one kind of takes precedence?
So if
Nope.
you have the maple integer, ring of maple integers on one side and the ring of.
That won't. There's no
Singular.
canonical coercions. Because canonical coercions have to be defined on the whole domain. And
Yeah.
there's no map from the whole domain of all maple objects to all singular objects. So
That's the way it is. Other systems, it's the ring of pari objects.
I know.
It's a free Z module on how many elements with a lot of relations.
So just about what Martin said about
Right.
execution speed, the way I think about all this is for convenience when you're just trying to write some code quickly and you don't really care so much. But I guess as soon as you start really caring about the speed, you probably want to start being more
Yeah.
precise about your types anyway.
So there's a coercion profile. You can turn on the profiling, run a piece of code, and it'll tell you all the coercions that were done and how long they took.
yeah. What's the function name to do that again?
You have to set up, it's not a function yet, you actually have to create the object and instantiate it as the coercion thing, you should make a function for that.
Yeah.
So that's really handy when, because the thing is, typically in code, when you have a bunch of things, eventually they'll all coerce down to the same thing and then you'll be doing arithmetic there. But sometimes you'll surprise yourself by, you're constantly coursing an int into your, rationals and, yeah. So you can write code and then you can look at what coercions are happening that you weren't expecting.
Do you have that document, how to do that?
Yes, I do. There's a big doc test documenting it.
Well, otherwise the path wouldn't be accepted.
So I want to make a function that you can just turn it on and off, kind of like a global proof thing.
Yeah, I would like to use it.
Yeah.
Yesterday.
It was there.
It was inspired
the code, I remember now.
Craig Citro, and we were trying to figure out why the code wasn't as fast as possible.
Oh, is this
And there was like we were like trying to manually say which of these variables at which time is an int that's turning into an integer that. Yeah.
This was the thing we were writing in the lobby at Palo Alto?
This was actually, I was on IRC with you. It was
Oh,
the Q expansion, I believe, was it? Or no, your Einstein series?
Oh, okay.
Eisenstein.
Yeah,
Eisenstein,
Eisenstein
yeah.
series. Oh, yeah, I remember.
So, and then here's the hard case, that's the interesting case, is when there's some canonical thing that both of them coerce into. And I call this the push out.
And Z is mysterious.
Yeah, Z is a mysterious push out that's a little bit abusive notation at this point.
Because in every other case, you already knew the inputs, but now you don't. Or I mean, you know the objects involved.
So, kind of the way that you can look at this is a lot of things you get are really just applying functors to simpler objects. So, for example, this right here is completion of P, and then you join X and Y. You start with the integers and you just do those two functorial operations. Here you've got, take the integers, you take the fraction field, you take an algebraic extension, and then you take a polynomial ring, and then you complete with respect to T. Same thing here, you take the integers, it doesn't matter if you take the fraction field or complete first, and take the matrix. And this gives a good perspective for trying to find this mysterious push out. So I'm going to call the construction ring the series of rings or construction tower. This, I think of this mostly in the context of rings because it has a lot of interesting examples and non-trivial examples, but this applies to any kind of parent. You do it for groups, obviously fields, more complicated things. So it's this tower of things, the sequence of events to get to your final ring. Yeah?
Controversial example. Take a polynomial ring over Q and take a number field. Since this number field is given by adjoining the root of a polynomial, this number field is a quotient of the polynomial ring. So hence there's a coercion from this polynomial ring to the number field. Going to the scalar by basically evaluating it at the adjoint root.
Danger.
And so, yeah.
Now we take the number field and take the polynomial ring over that. And we take the polynomial over Q and we want to coerce that into the polynomial ring over the number field.
Yes. And so the answer
Polynomial
there,
rings are not
well, the short
always-
answer is we view algebraic extensions as an atomic operation.
Okay.
It's not adjoining something and taking a quotient.
It's one thing to keep.
Yes.
It's horrible, but yeah.
You can think of it as a quotient of a polynomial,
Oh, and
but the variable for that polynomial is just...
That's another way to say it. It's a variable have to match.
Since you guys have variable names, you might actually be okay.
Yeah.
We have very
So
Sage in magma this goes.
the thing about
Wait,
push
wait.
forwards, the reason it's kind of a
What happens in magma? What happens
In
in
magma, this can actually go wrong. This particular example, I think, actually does what you'd hope it does. But so, I mean, it can really get complicated.
So to make sense of a push forward, you need an initial object. And the other thing you need is a category, which you want to do these things in a category theoretic context, but it makes it really hard because really your things don't belong to the same category necessarily. You have the rationals and you have the integers. And they're both rings, but the result is a field, and you want to have field morphism. Basically, you want to have field morphisms from things coming from a field, and ring morphisms from a thing coming from a ring. And so it's still a little bit fun thing to talk about push out. Why did I say push forward?
Because you're writing the talk as fast as you
really
could.
fast. Yeah, at least I'm saying the right thing. So you need an initial object to talk about a push out. So so the way we construct initial objects is we look for if we take our two things and we look at the construction towers and we see if they ever converge.
Conversion means coincide.
Coincide, yeah. And for instance, for rings, if everything has been implemented, most rings go all the way up to the integers. You start with the integers, and then you do a bunch of series of operations to get down to something more complicated. And then for a couple cases, most of this is because it's just not applied yet. You might have two towers. The first object that you know about that everything descends from is not. So you might have like R, and then I'll call these so you might have R and S, and if these don't match, then what you do is you look for a canonical coercion, say, going like this. And then what you do is you consider this to be the initial object. And then now you're trying to find push out between R and S with respect to this initial object here. So, the way to look at this is you want to merge these two towers by applying the functors we got from here to here, here to here, here to here, here to here, and so on. And so I'm going to do an explicit example. First, kind of the way we were thinking about it in Sage Days 4, and then I'm going to look at how we simplify it. So let's say I have, and then I also have like that. So this is the matrices, 2 by 2 matrices over Q, and
Those both go back to Z, right?
what?
Those both go back to Z.
Yeah, so both of these go back to the integers. like that. So the original model was looking at, for instance, these two things and saying, well, how do these go together? And then you say, well, how do these go together? This is Q. And then how do these go together? And then finally we get like that. And so if you look at this, kind of when you start playing with things, the original thing you think of is you think you want to do all these base extensions. And so right here, we have a base extension. And right here we have kind of a base extension. Well, this isn't base extension so much as, well, okay. Right here we have a base extension. Right here, clearly we have a base extension. Right here, we have a base extension. And then it's kind of unclear to say, well, what's like the base extension with respect to this thing here? Does this have like a base ring of Z, and then we're making the base ring be ZP, and you get that? After playing around with trying to implement this idea, I realized that there's actually a preferred pathway to go through this diagram to get from the top to the bottom. And that pathway, in our case here, is actually you go like this.
Whoa. Whoa.
Does that make sense?
Each thing's one of those atomic operations.
And there's exactly one pathway.
Whoa.
Yeah, what's
What's special about that?
So the special thing, well, actually, this could go either way depending on whether or not you think completion or taking fraction roots has precedence.
You're just assigning precedence to these different.
Exactly, I'm assigning precedence. And but the precedence, notice, avoids all base extensions. Because what a base extension really is it says, take this, go up the tree, apply a functor, and now apply the functor I had originally. So base extensions are always going up the tree, some indeterminate amount, so you can come back down a different way.
That's why they're hard to do.
Yeah.
Yeah.
So the question is, how do you figure out this this thing? And the answer is you just assign precedence to each one of these operations. And you can say that things are allowed to commute if you want. And then
as soon as you have any path, you're okay.
And then the thing is, what you do is you start. You start out. So the thing is, you start out with. I'm gonna kind of draw. So instead of creating this whole grid, so you start out with
A spanning tree.
this, and you go. This one comes to. And this one was. And the really important thing is the functors here. So that's P completion. This is frac. This is join X.
Over Z.
This is. This
I mean,
is.
I mean, if
So
it's
Did you just write
one
this?
is
This is
not
just a
there.
particular set of things.
Oh no, this was the end of my
basic
thing.
essentially
Right.
something where
Just for clarity, could you write the two elements that you're adding together, where
Yeah.
this exact diagram comes up?
So
At least the two
my elements might be,
elements, right?
well, it's an element of this. So I might do X plus. Sorry.
Well, not X.
Yeah.
Yeah.
X being an element of this
Sure.
thing.
Okay. Good. Thanks.
Yeah. So it's ambiguous to write the elements.
And it's very nice that
But we don't want that to work, do we?
it already does work.
So
Why?
this is the debate about whether or not there should be a coercion from the base ring of the matrix to a square matrix.
Well, do
Well, but there's
multiplication
other-
to avoid that.
What?
Use
Yeah.
multiplication
Use
to avoid that.
multiplication, yeah.
Okay.
Because everybody agrees that we have
So
to do that.
5 for 1.
Yeah. Make everyone happy, except for this doesn't happen this way because it's a scalar multiplication.
Yeah.
So how do you know you don't want a? Oh no, I suppose it's the same. Okay, sorry. My other question was, why is Q to QP not a base extension?
So Q, what's the base string?
Well, what's the base string in this example you have below? The matrices of the Q, the matrices of QP.
The base string is Q here and QP here.
No, Q. Why isn't Q to QP a base extension? Isn't that just Q tensor ZP over Z?
Right.
Well,
That's
yeah,
a base extension to me.
you can view it.
I mean, maybe base extension
problem.
in like the mathematical sense is not necessarily the word you want,
Okay.
right? You're saying somehow for you it's anything where the most reasonable way to do it is to go completely back around the square.
Yeah.
Yeah.
Which,
Right.
the most canonical example is when you have polynomials.
Yeah.
You want to do something like this.
Whoa, so you're saying to go from Q to QP, it's more natural to go back up to Z and go back around.
No, wait,
Well,
he's
I
saying it's
actually,
not.
I don't remember which one of these two things should take precedence.
Yeah.
In fact, I think it probably should be the other way around. Maybe.
Yeah.
But no one has complained yet, so whatever order I picked seems to be good enough. Like that.
Okay, so, sorry, let me just try another example. So you're saying to go from ZPX to QPX? The most
So-
natural thing is,
Is to go back.
I don't understand what you mean by go
So-
back.
So where
Actually,
did this
don't either.
Q come from? Where did this QP come from? It came from ignoring the fact we were a polynomial ring and doing something and then readjoining X.
Okay. Ah. So you mean it's like acting on each coefficient?
Yeah, it's acting on each coefficient, but it's saying go up to the base ring,
Matrices as well.
do something, and then come back down again.
I mean, I think base extension is probably the wrong word, given that in the top square, all of those can be written as tensors, right?
Yeah,
So when you say base extension, that's what people are going to think.
yeah,
I think Z,
I don't,
What about,
ZP going
oh,
to
no,
QP
that's not
is
what you-
similar
Yeah.
to
so,
that one.
so to work through this example, instead of creating all, this is kind of a quadratic time algorithm to fill in all these things. But the thing is, you only need to fill in this path. So what you do is you start out with your initial object, and you say, which one of these has higher precedence? Should I complete with respect to P first, or take the fraction field first?
So I think fraction field should be first.
Yeah.
So then I take the fraction field,
So the path you,
and do
the
that.
previous one, I
So
think
it
was
should be,
better.
in this example, it doesn't matter what you pick, both of them. The two operators commute, so it doesn't really matter. And then what I do is I say, should I complete with respect to P or take the matrix? And this one has higher precedence. So then I get like that. Then I say, well, should I adjoin X, make a polynomial ring, or make a matrix? And polynomial rings take precedence over matrices. That's just because, I don't know, we tend to prefer matrices with polynomials rather than polynomials with matrix coefficients. So,
Matrices are non-commutative.
yeah, that's another point. So now I've taken care of this, and I've taken care of all these, so my only choice now is to make a matrix. And I arrive at the final thing where I've applied all of these functors. Now, there's a couple of other cases where, for instance, I've got,
So basically you're assigning, I mean, what you're doing is you're assigning a precedence order to all of the functions that we might have thought.
exactly.
And you're just always working based on the precedence order. You say, look at where I am, look at where I need to get to, I have things left to do, what's the best, what's the smartest thing to do according to our precedence order?
And you only look at the top of the
Right.
things you haven't done yet. So for instance, I could have had I don't know if you can read that. This is the fraction field of polynomials over X in QP. Now that would have gone right here. Well, this should have actually been here because these were my originals. Now this right here is higher precedence than, for instance, some of these other things. But I don't even look at this one until I've already done this and I've already done this, and then I want to do that one.
Why is Z adjoin X not on your picture?
Z adjoin X never comes up because we avoid it. We go down this path like that.
Yeah, but when you constructed this diagram, why did you not consider the functor adding X on first as one of your options?
Because to get here, I have to pass through this one.
But you could take Z adjoin X and then base extend up to ZP. I mean, that's...
Well, that's the thing, is base extension is not a functor. Well, when I say base extend, I mean...
This is the wrong one.
I don't know what to call it.
It is a functor.
yeah.
Tensor.
ZP to QP is base extended. Because
Yeah.
you think ZP as power series and P.
Yeah, we just tensor.
Yeah.
It's little localization.
Yeah, no, I mean, everything inside can be written as a tensor product up there. Right? I mean, Q tensor M2 over Z would get you M2
I guess-
Q. You know, you could keep doing it.
What I'm saying is, you said before this is quadratic time, but I don't understand, like you have to sort of examine all the possible functors. It's more like exponential in the number of functors or something.
No, so this algorithm here would be quadratic. Well, you have to construct a quadratic number of rings. Oh, so there's something, every
Quadratic in what?
quadratic in the number of rings you have to construct.
No, it's linear in the number of rings you
It's
have
like
to
the
construct.
answer
Right.
message passing.
Oh, in the number of rings you actually have to construct.
Every ring has to talk to
Oh.
every other ring.
It's worse than that. Like, I mean, you know.
Yeah, this is why we use track.
Yeah. So versus this right here is linear.
Every ring has to communicate with every other.
One ring to bind them.
Okay, so there's something that maybe will make this more clear. Every ring in Sage, or every object in Sage, has a construction method that returns a function. So this right here returns the functor p completion in the integer ring,
Okay.
such that calling this on this returns self. And that is just defined however you want. And it seems natural to say, well, what's this? Well, this is created by taking this and adjoining a variable, making a polynomial ring. So that's where this thing comes from. Even though you could like go up other paths, there's a I guess choice made that the construction of this is taking this and adjoining a variable.
I still don't understand. Like there are other options now I think about it. Where are matrices over Z? That seems to be like it should be on this picture somewhere.
He's saying that if your ring is ZP adjoin X and you type R dot base ring, you're gonna get ZP out. That's how he's getting the things.
Here, let me actually.
He started out with a ZPX polynomial.
Yeah.
And
Yeah, so
a
I
matrix
have.
over Q.
Yeah.
Yeah, so when
So
you hit
those
base
are the
ring, it's
two.
gonna say Q.
Yeah.
There are no matrices over Z.
I know, I'm just not, it's not clear to me where this picture. So you're saying, to get this, the algorithm for drawing this picture on the page is take the two rings you started with,
Uh-huh.
keep following up their parents up to the top,
Uh-huh.
and then generate all the stuff in between.
Yeah.
Okay.
So, and you can see that here I have, say,
Oh, I see what you're saying.
So that X, the coefficient of that X is the 1 of ZP.
Yes.
So it never can go down to be X
So
with coefficient in Z. It can go up to be Z X with coefficient in QP.
yeah, so there's many ways to create these things, but once you have one, this is kind of a choice of a canonical way to go back up to simpler and simpler rings.
and does everything always go back up to Z?
No, because this thing is not necessary just for rings.
But for rings, okay.
For rings,
I mean, it should,
it
it's the initial
should.
object, right?
So
if
there
the
should be-
construction function is written.
Okay. So there are things that are kind of endpoints in this chain.
Yes, there are, for instance, number fields right now, n, because the algebraic completion functor is not written.
What does algebraic completion mean?
It means you
Not-
want to adjoin a root of a polynomial.
Not completion.
Extension.
Algebraic extension, sorry.
How does this plan mesh with the stuff that we were talking about before about about being able to specify canonical maps between objects.
So that will come later. Yeah.
As perhaps as fast as if I just write the example or like the way you were thinking on that one. Suppose we start with polynomial.
Here, I can erase this, right?
Yeah, I think so.
Yes, I was about to say. Ooh, why do you do?
That's only the
This is how
beginning.
they're constructed. It's a
Okay,
polynomial
yeah.
and a polynomial.
Uh-huh.
How they're represented.
So you're doing it backwards of what I was writing.
No, this is the tower that's given to you.
Yeah, no, he's saying put the diagram.
I'm saying my tower started at the top.
No, he's
No,
He's just-
this is what's constructed.
he's saying consider the following problem.
Yeah.
X,
No, I
Y,
think
Z, Y.
the
Whoa,
issue is
that
that
wouldn't
whoa,
work.
You cannot
You have your-
join
Nils,
Y.
Your
X, Y, Z,
orientation
Y,
is-
X, Y, Z, Y, or X, Y, Z, W in the very top
No,
one.
there's going to be two Y's there.
Two Y's.
Yeah.
Okay,
That would be okay.
really.
Yeah, but where do you end up?
What does it mean?
Okay,
And
so
which
then,
Y, which is the Y for F?
so this Y would get bound to this Y because
Because
it
it
would
has
look at
the
these
first.
two things. Like originally it would start with, so this is actually, there's a couple of times when it can't,
That's good.
this precedence runs into problems. Precedence runs into problems when the two functors here are equal. So say I did p-out completion here and I did p-out completion here. Then it would say if the two functors are equal, just apply it once. You don't apply it twice.
So ZX plus ZY.
So that, but zx and zy
They're not identical.
are not identical.
Oh, okay, because it's,
Yeah.
oh, because we care about the name of the.
Yeah. So then what it does,
No, there should be a problem with things like that.
so so let me do an example involving polynomials, and then we can look at this. So
Can you say what the arithmetic operation is? Or
it doesn't matter. Actually, all of the coercion doesn't care about the arithmetic operation.
So what are you doing? You're adding something in
So
ZY
I'm
to
adding
something
y
to
to
X?
x where they
Okay,
live in these
that's
groups
what I mean.
respectively.
Yeah.
Yeah, so.
I mean,
Like
the
this.
expression, yeah.
So what it does is it says, well, should I add y first or should I take the fraction field first? And it says, well, I should take the fraction field first and get q. And then what it does, so this is done, it says, should I add y first or should I add x first? And it says there's an ambiguity. So I say I'm just going to give up because there's no way to resolve it. Now, if, for instance, it was like this, it says, should I add y first or should I add x first? And it says, I don't know. Maybe later on here I add x. Or maybe later on here I add y. And it says, oh look, I'm adding y later on. So these two are probably the same operation. So this is,
But, okay, so.
and so I'll get to your example. And so what it does is it adds x.
That shouldn't be.
No, no, I'm
X,
even
Y.
more
That should
worried
be
about
join
this
X,
example.
Join Y.
Let's say,
Okay, let's say that it's
Okay.
back. And then, so this goes to q adjoin x adjoin y. And then it says, now do I want to add y first or do I want to add y?
Oh, hang on,
No,
hang
no,
on.
no, you have two.
Just
join
one
X.
step at a time.
Yeah.
It just does X first, right?
It just does x first. Yeah, sorry. And then it says, should I add y first or should I add y first? They're the same thing. I'm just going to add y. And there's your result. So here,
so what happens when on the other side you have adjoint Y and then adjoint X?
yeah, you mean, oh, if there's an adjoint x down this way,
Yeah.
yeah, then it blows up and says it's ambiguous. Because I don't know which one to do first.
Wait, so I'm curious,
Yeah,
I
but
mean,
no,
in that example, it would search, I mean, how does that actually, so it would look and it would say, do I want to join X or do I want to join Y? I don't know. It needs to look to see, does it just check both ways and only if it gets one response does it decide to keep
Yeah,
Take-
exactly.
take it on
It
faith?
says, look, I'm going to be adding y later on, so I'm just going to postpone that y.
But I mean, it also has to decide whether or not it's going to be getting X later on.
Yeah, if I'm going to get x later on and I'm going to get y later on, I'm going to be in the same boat later on, so I might as well throw an error.
So you're basically, instead of trying to look at this from like a mathematical category 3 point of view, you're taking the position that every parent object in Sage is a result of a finite list of constructions.
That's
each
the
of which
perspective.
each of which has a short description, and you're just matching lists of descriptions and trying to come up with something that formally sort of makes sense.
And you're imposing a sort of order of operations.
Yes.
Which,
That's nice and simple.
I mean, that's it.
And it seems to work really well in practice. It gives you what you expect. Like it gave that whole list of things from
And
the
it-
example from
And it
Sage 4.
seemed to easily give the random challenges we threw at you too.
Yeah. So in this case, what would happen is it would say, oh, look, I'm going to adjoin x first because I know y is coming later on. So I get, and then up at this step, it'd say, I'm going to adjoin y. And then it would keep going up this way and end up here because there's nothing more to be done on that side.
The Y would end up, the Y on the left would end up as the first Y on the right.
It would end up as being the first, yeah, bound on the inside, kind of.
Is there a function in Sage now that given to rings gives you back this that's available at
Yes.
the top level? What's it called?
It's called push out.
Oh.
Yeah.
I don't know
Bradshaw
if
happens
that's
to
a
be a
good
technical
name.
term in
And
mathematics.
I couldn't come up with a better name, but I am welcome to have input.
The other thing, well, yeah,
Coercion destination.
I don't think I like push out. It's yeah.
It clashes with mathematical.
Yeah,
Yeah.
but apart from that, so what happens? So you're sort of
Cylon.
assuming that what?
Could call it Cylon.
You're sort of assuming implicitly that it makes sense to permute the order of these
No.
operations.
No, it doesn't.
You always do them in the same order.
You only look at what's next.
Oh, so
Yeah.
you're sort of getting around the problem of these functors not commuting with each other.
Yeah, because you might have you might take something here that's really low precedence. But if you did all this stuff, like for instance, if you take the fraction field of this thing,
Yeah.
you have to end up with the fraction field of a polynomial. Even though fraction field has higher precedence. It has to come after this one.
It's only for deciding each step.
But it's still true that if I start with a ring and apply some sequence of operations in some order,
Uh-huh.
then the tree you would draw might not have those operations in the same order. Is that true?
It will have the operations in the same order, but they will be merged together.
Well, like for example, suppose I have a functor which is like p-adic completion.
Uh-huh.
So suppose I start with z. I could either go p-adically complete and then join x.
Yeah.
Or I could first adjoin x and get zx, and then p-adically complete that I should get zp adjoin x. Do I get the same object? Like, and is it going to give me the same sequence of parents?
Well, so okay. So
Like what I mean. So what I'm really asking, the p-adic completion of zx, is it zp adjoin x, or is it the p-adic completion of zx?
Well, it probably will
There-
give you an error right now. in
I'm
polynomial
sure it'll
so
give you
on.
an error.
Okay, sure, I'll give you an
Yeah.
error, right? But in an ideal world, if this thing worked, what would you want it to return?
I would probably, I don't know.
What operations are you trying?
He's trying to periodically complete the ring z adjoint x at
Oh, yeah,
the
I'd like
prime
to
ideal
do that.
p.
Well, the thing is, where you
That's-
how many times you just want to get
I mean, it's-
z adjoin x, so you can just.
Well, no, that's not what the completion is. The completion
Yeah.
is, something that isn't otherwise defined.
It's not
power
zero.
series with coefficients that converge to zero.
Oh.
Yeah.
Yeah, that's the thing. It's different.
Well, can someone else come up with an example of what I'm? If
Well, I
no
don't know what
example
you're trying to come
exists,
up with.
I'm trying to come up with an example where you write down some sequence of constructions from z, and you get some object. But then when you ask it, what is the sequence of parent constructions, it goes back to z, it returns you a different order.
Yeah.
But why would that be a problem?
Well, I mean, it's just that.
I think the question is, are the two bottom things canonically isomorphic? Just because they were constructed in different ways.
I mean, this is supposed to return the canonical construction, right?
Okay, what about take power series over z
Uh-huh.
and periodically complete that? Does that give you Same thing. Is that could be power? No.
Power series over Z.
Then, yeah.
Mechanically complete, that gives you power series over ZP.
Okay, so that's what I want.
Series over ZP. Okay.
Yes.
And is that compatible with just taking the projective limit of Zx modulo Pzx to the power n?
Wait, taking so the polynomial ring?
Modulo P times the polynomial ring to the power n? I mean,
No.
that's an
No.
ideal.
No,
It's
that's
the P
different.
comma
That's
X, it's the
yeah.
P comma X additive completion.
Yeah.
It's not the P additive completion. Those are different.
Yeah.
So, right. So I've got these two different ways of constructing this, and I should get the same Sage object, right? The same class, the same whatever. But then when I say when someone tries to use this mechanism to build this sequence of codes,
Yeah.
it could end up picking a different one from the way I actually arrived at it, which seems a little strange.
Yes.
Like, I can't see anything immediately wrong with that, but it just feels a bit weird.
Yeah. So the thing is, you would have to have information about remembering where you came from. That means you would have to actually get a different ring.
Yeah, you'd have to have that information.
Yeah, if your rings tracked how they were constructed. Right, when you make a polynomial ring, it stores the fact that I just made my, like, if every ring has attached to it a chain of rings backwards.
Actually, I think it's a problem. I think you just have to impose the axiom that whenever you construct an object like that, it always just rearranges itself to be in this kind of tap. So it just when you
Yeah.
I mean, there's no problem. It just you take the p-adic completion of ZX. If there's some clever code in there which says, "Oh, cool, I'm really these power series over ZP," and from then on, that's what it is. Yeah, I don't think so. I think it's a problem.
Okay, so
Right. The problem is when they don't commute. No, because then you went, no, that's okay.
You just,
You'll just get different objects.
yeah, if they don't commute, you'll get different things.
Yeah.
So then the other thing to look at is multivariate polynomials are handled by, it treats it as a single variate polynomial. And then the functor here says add y as a multivariate polynomial with what's already there.
Ooh. Oh, so that it knows to deal with that differently than if you a priori didn't know that things were.
So that this thing is different from q adjoint x comma y.
Yeah, I agree. But when Q adjoint x, y, what's the next step up? Is it Q?
Because it'd be q adjoint x, and this would be y.
No, q adjoint x comma y.
The next step up is
the order.
Oh, it's a different atomic operation.
So
it's
then
it's the same operation that has different data attached.
So presumably it's a
Okay,
Yeah, yeah. And the same thing, for instance, with completion.
Oh, the same.
You can complete it at infinity and get RDF, or say the real field on 53 bits of precision over MPFR. That's different information that's attached. Yeah?
So let's say I have q x comma y, and I have, let's say, q y comma z. But x, y is lexicographical term ordering, and yz is stack reflex ordering. And the funny thing is, if one of them is lexicographical, you could actually do it because you can use block orderings.
Yeah.
I'm not sure if you can do it in any case, no, but you might. I'm not entirely sure.
Oh, he's going to try it.
It's just fine, it's right.
But you probably didn't implement anything having to do with the
I
term
didn't do
order.
anything having to do with term ordering.
That makes it easier.
Yeah, I could have told you it was that fast.
And notice this is not ambiguous because there is a definite order to those terms.
So multivariate
Yeah.
polynomial ring has an order.
Yes. In Sage it has an order because, for instance, the call method takes parameters in the right order.
Yeah. Grub bases might not use that order for their reductions, but the
So
generator
you're
still
always
a 0,
ordering
1, 2. So
Yeah.
If you just did, if you did that same thing, what you did s of s dot z comma y.
Yeah, so I'll do that.
Yeah, it's how you do with the names.
Oh.
Because what comes first, the Z or the X?
Just think about what the pre-pressures do.
Wait, it's hard to see because of the scroll bar.
Yeah, scroll back.
Oh, sorry.
Oh, it has to intersplice that Z in between, and it doesn't.
Yeah, well, it
do
does.
that.
Well, does it put the X in between or the Z in between?
Yeah. Okay.
There's an ambiguity there.
So that other ring in the three variables that you just constructed, which I
Uh-huh.
suppose has now been destroyed, but anyway, you can like coerce elements of S and R into it.
Yes.
Okay.
So this is back reflex right now. You just ignore the term ordering and you always construct back reflex.
Let's just .gen 0, .gen 1.
Yeah.
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 You only have to
actually-
order the variables themselves.
So another approach would be to have adjoining multiple variables be a single
Yeah.
atomic construction, and then have ways to merge those.
And that actually, because then you run into, like, how would you do, like, this, then you have to look further down in your tree.
Mm.
And it makes this algorithm more complicated because you can't just look at one of these at a time. Like, if this is adjoining three variables here, you might have to, like, go down here and see if you're adjoining those three variables in the right order down here. It just makes things a lot more complicated. It will come out as 3 in a row, but you only have to worry about one at a time. And then you can do stuff like, for instance,
So in particular, Q adjoin X adjoin Y is not compatible with Q adjoin X, comma Y.
The Z is no longer defined.
Huh?
Z is not.
oh, yeah. So,
So you cheat. Okay.
actually, yeah.
Cheat is more interesting.
Because there's a non-ambiguous ordering of those things.
Why did it add B?
Well, I added, so this is X, Y, A, and B. And this is Y, T, and A.
It doesn't have to put it this way.
Oh, sorry. So this is X, Y, A, B. This is Y, T, and A. And
Yeah.
that's the only place T could go is in the middle here.
And that's just being noticed because of this algorithm. It's not,
Yeah.
it's not actually doing anything. Okay, yeah.
I think that's fine, right?
Yeah.
That's, I mean,
Yeah.
as long as there's a well-defined rule of how
Yeah.
these things happen.
There's only one thing that can be returned. Yeah.
What I'm worried about is that, I mean, did you try how this operates if you also throw quotient operations in the mix?
Yeah. Well, I mean,
Like taking quotient objects.
so,
Yeah, taking quotients of that.
Crazy stuff.
Oh, Pete.
that's probably because so that should probably have worked, but something's not implemented yet. This thing hasn't been implemented for every single ring.
No.
Yeah.
Okay, now a three-dimensional vector space and a five-dimensional vector space.
That would be an error.
Because there's no canonical coercions.
Well, there's a
implemented.
canonical coercion of the
Is there?
three-dimensional
Is there?
vector space into the three-dimensional times the five-dimensional one. If you throw Cartesian products in the mix.
Well, the tensor
When I say
product
there, I
is
mean,
into the 15-dimensional.
But hang on,
it's
hang on.
different.
No, the
Just a sec,
three-dimensional
just a sec.
times the
Just a
five-dimensional,
sec,
not the
but the
15-dimensional.
algorithm is, if I understand it correctly, is the algorithm is ask what is the base
Yeah.
object, the base is say Q or something, and the operations are give me a three-dimensional vector space over Q or give me a five-dimensional vector space over Q, and it looks at those two things and it just doesn't know what to do. There's nothing to pick first. So there's nothing to do.
Yeah.
Yeah, you can't take a five-dimensional vector space over the three-dimensional.
So can it go wrong if we
It's
throw in
not-
some
It's not canonical
Cartesian
because
products then?
it depends on how you
Right,
Order it.
order it.
Yeah, is it the
Right.
three
Right, because
How
it's
you
five
order it.
times
So
five
is
dimensions.
it 5 copies of
vectors of dimension 3, or is it 3 copies of vectors of dimension 3?
No, I was saying actually construct the Cartesian, just the thing called the Cartesian product of the two vector spaces.
Right, but in what order?
There's no order in the base, and vector spaces so far have order for base. Or they don't have a canonical
No, but there could be a category of Cartesian products of vector spaces.
No, but if you do the 3 plus the 5, where do you want that to live? Or the 3 times?
In the Cartesian product of the 3
In which order?
dimensional and the 5 dimensional.
Okay, but there's an ordering there. Cartesian product 3. So that means that addition isn't commutative.
No, addition is what?
It is.
Yeah.
But the
Addition should be commutative.
Yeah, that's that. I prefer it that way.
Yeah.
But what you just proposed, addition,
Yeah,
wouldn't
so
be.
so
commutative.
it's ambiguous what the
No, because he
coverage
wants to
structure
do
would be.
Z3 tensor Z, or Z3 cross Z5 for if you do A plus B, and you want it to be Z5 cross Z3 if it's B plus A.
Yeah.
Yeah, it's ambiguous which thing is.
It's the up down from Bill's talk.
Yeah, but what would work is a 3-dimensional vector space over F3 plus a 3-dimensional vector space over F9.
Hopefully.
Yeah,
So-
that should.
Which should work.
Is a
Yeah,
power
But that should work
series,
just from canonical coercion.
Yeah.
is a power series an atomic operator? Call me a power
No,
series.
it's not.
It's not atomic. You want it to be a completion.
It's completion. Yeah.
Completion of polynomials.
Uh-huh. Is that bad?
No, even with that example, you have to be careful because that one 3-dimensional vector space might actually be a 3-dimensional subspace of a 5-dimensional space.
It remembers information like that.
Well, I think he was thinking of free modular
I was
rank
thinking
3,
of free modular.
Yeah,
not as some
yeah.
3-dimensional space.
Not,
So
not
now
a
there's a
particular-
It's like the
between
ambient one.
subspace,
Yeah, the ambient 3-dimensional tuple space.
Yeah.
Yeah, sure.
Yeah.
So, but that means that subspace, because that means that subspaces are
I feel like
less.
we're talking about just the like easy canonical coercion suddenly.
Yeah, I'm just trying to think. I mean, it just looks like a system that should break in certain cases.
Yeah.
And
Well,
it's
also-
sort of essentially so, because I think it's fundamentally a hard problem. So any strategy will come up with breaks.
But this seems pretty practical.
This-
Yeah.
So I'll tell you
That's
this
not-
amazing
I'm not saying it's
practical.
against it.
There's a
Sometimes we need
subspace
new words
operation.
instead of push out.
If I remember right, there's a subspace operation. So it
Yeah.
goes to the ambient space on both sides, then it constructs the appropriate ambient space, and then if the subspace operators match up.
Yeah. So it's really a syntactical matching up.
Yes.
It really is,
Yes.
it really is, and I think
Yeah.
that
That's good.
produces what you expect.
Yeah.
Mm-hmm.
And if you want fancier stuff, you'll have to do that.
Well, you should do it by hand if you want to specify what you get. Yeah.
I mean, yeah, it's interesting.
Why is power series not an atomic operation?
Because I'm guessing it's because you want to be able to do something like Q adjoin X adjoin Y. You want to add that to something in the power series ring over X, and you want the X's to match up. So you want it to first go, oh, they're both polynomials in X, and oh, that one also a power series. Push it out to a power series.
Yeah, and why? So I missed the first part of the talk. I don't know if this was a term that was discussed then. Like, so is it, how do power series fit into this picture?
They're completions of polynomial rings.
Okay. I don't know.
Yeah. So that way it matches other variables, and then.
Okay.
So dot construction.
Oh, right, yeah. And
What does that
the
do?
completion itself will take precedence over adjoining another variable.
Exactly.
Yep.
At least we think it will.
Yeah, it does, I tried it.
So you've implemented the X-adic completion, is that?
Yes, well, it's really, it just,
Wow,
the
completion
polynomial ring, when you call complete on it, it says, oh, I know how to complete myself with respect to my own variable.
With respect to my generator.
With respect to my generator, it returns the power series.
And if you do it with respect to
Yeah.
X minus A,
Then it says, it throws an error.
Wow.
if not implemented error.
I don't know if it's not implemented, I think it just, well, it'll come out as a typo.
Huh?
Well, it should, not necessarily, like, if, the version code only catches type errors. It doesn't catch not implemented.
I think it, well, I think for completions it catches not, like I think for these functors it catches not implemented errors.
Okay.
Yeah.
So if Sage ever gets multivariate power series rings, or do we already have them?
No. We don't.
No. Then it's adjoin the first variable complete, adjoin the second variable complete.
Yes.
Well, but there's different ways to do it, right?
No, it's just that
mathematically it's the same object.
Yeah.
So in the end.
And the order is determined by the order you type it.
Yeah, that's probably fine.
Yeah, and this
Isn't it different from-
when you join the second variable, would know there's multivariate.
So it would tag it that it actually has to be this.
Yeah, because it tags the second variable as being multivariate. Yes.
They're different topologies, don't they?
Yeah. But they're not very
Algebraically they're the same.
We're just dealing with that.
So anyway, so if this
In terms of coercion, we're already dealing.
is all the controversy we're going to have, then I'm pleased. So there's going to be a lot worse stuff.
No. We just haven't thought of how to break it yet.
exceeds any other model that people can think of, I think. So.
I liked it
Try
so
break
far.
it. I mean,
It's the worst thing we have.
So Nils, how does this?
Also,
What is the magma model, anyways? I don't know if there's a magma model, but is there one? I've never been able to figure out if there was one.
No,
or not.
I don't think, because if you build your tower sufficiently high and there is something in the bases that's compatible, it can sometimes forget about it. So things are not transitive in the way you'd expect them to be. Because sometimes it's just too hard for the system to figure out.
Is there some central code that tries to figure out?
I have no idea, no.
Because like in all the code I've ever read, I just remember overloading star and just like, doing a few random things and that was it.
Yeah.
But okay, there's nothing. So your talk is entitled "Why Base Extension is Wrong." What's the summary of that? I mean, you tell us why something else is better.
extensions is the
so
things
base
we avoid.
extension in
And
the
also,
sense of,
yeah, it's not really basics.
yeah, like it's called, people call it a base extension. There's probably another name for it that's more mathematical.
What is it? It's going up and down.
Yeah, it's going up and down. It's saying I have a polynomial over
Yeah.
this, and I want a polynomial of the same variable over something else.
Yeah.
It's a heavy-sided square.
So it's extending the base string.
Yeah.
Okay.
Is probably a better way to say it.
Scalars.
And the thing is, with this
Well,
method, you
it's-
never
yeah,
end up
extension scalars is
extending the base
base
string.
extension. I mean, yeah, that's bad.
Yeah.
That's too many other things. Yeah, I mean, I think the only thing you need are two new words. One for what you were calling base extension, and another for what you were calling push out.
Well, we're getting rid of base extension, right?
Right, but you
And
need to
push
say
out.
this is the thing we try to avoid.
Yeah, yeah.
Okay.
And what do we want to call this push out function? If you don't want to call it push out.
The thing that computes the way
Yeah.
to go.
Uh-huh.
Force out.
Peace out.
Covering structure.
Canonical coercion.
That's the best one so far.
Bradshaw.
Well, that's,
What is in that?
that's the memory term. But
So
it's got strange semantics.
Right.
Also, because you can parse that the other way. Bradshaw.
Covering parents.
So what's exactly the difference between these and what implemented after Sage Days 4, other than my code is a mess? But
So the difference is that it can handle more than just polynomials and matrices and stuff that has an explicit base root. So for instance, it can handle.
I mean, really, it's a step at a time viewing of what's going on. I think.
But that's what we were doing, I think.
Yeah.
It's just there were some. I think the problem is there were some canonical coercions missing between some objects.
Yeah, I mean, the thing is, it works with things that don't have kind of an explicit, this is my base ring.
Like what?
Like, for instance, a number field. Like if you want to add a number field to the p-adics, it will know what to do in that case.
So it's the same thing, but in terms of this construct function rather than
Yeah.
base.
Yeah.
So it's
And it's a lot, it's clear to see exactly what's going on.
Yeah.
You don't try go up one tree, try go the other tree, and
so you are going from down
You're starting with something and you're
I
just
was going the other
constantly
direction,
constructing
so-
it one piece at a time until you get to the bottom.
So a lot of these atomic operations with data attached.
Yes.
And that data can be dependent on the base that they're extending from.
Uh-huh.
So the example you just gave of a number field in QP,
Mhm.
how does it handle that? Because
It doesn't yet, but what it would do is it would say, it would create,
so the
I think the thing is it would create QP first, and then it would say, I want the algebraic extension with respect to this polynomial.
Right, but the polynomial, if you extend QP, the polynomial should be a polynomial over QP. So you need a way of.
But the integer is embedded. Oh, you mean you need to embed, yeah.
So
that's
your
true.
the data attached to the atomic operation needs to, you need to have canonical coercion there. Kind of
Yeah, that should be fine because you're dealing, so hopefully the data is simpler than the problem you're trying to solve.
Yeah, it should be. Because that definitely, to coerce that polynomial, you have to at least be able to do that step with the polynomials itself. So if you
Right, so you reduced your problem to a problem of coercing
Polynomials.
a polynomial over the integers or a polynomial over the rationals to a polynomial over.
Yes. And that can call this code and do the right thing and then you get back to where
Yes, and then so it can be recursive then.
Yes, yes.
Does this algorithm have the property that you have three objects and like an associativity thing? A plus B should land somewhere, and then you add it to C should land somewhere else. Do you get the same answers if you did B plus C and then you add that to A?
You might be onto
That's
something.
a good question.
Because I wanted to have that property, and the other property I guess is not as important. Is a reflexive sort of property where if you suppose you added an element to something in the same ring, but you actually called this system instead of just doing the arithmetic, right? So you actually drew the same.
Yeah.
So okay, so I guess
because,
really what
because the towers would be the same.
really so I guess really what the question is that means that we have to guarantee that an object can be completely described by the sequence of operations that led to it. Like what I mean is, if I give you Z and I give you a string or something describing the sequence of operations, you can construct the same object back again.
Yeah.
So that should be okay, I guess.
Yeah.
Well, every step is gonna match.
Yeah.
And it actually starts at the bottom. It doesn't go all the way, and it doesn't go any higher than it needs to. It starts kind of as low as it can.
Yeah, but the associativity one, that's interesting.
Yeah.
So
I'm curious if that can be broken.
Yeah.
I don't see any way to do it yet.
Let's say we have a divisor on a genus 3 curve over Q. Now we have, base extended that curve to Q adjoin I, say. Do we have an automatic coercion of that divisor that we had over Q to the divisor group on this curve over Qi?
No, what you do is you would write the construction method on the divisor function. With the data and the ring.
Hang on, what's the base object for
I think the base object would be the field. In that case.
And the object
The
that's
attached data would be like the defined
data
equations.
for
And then once you define that method on your curve, then we'll go.
This is the kind of constructions that get really painful because you know that there's a clear relation between the base rings of a construction, but you have such a big stack on top that constructing the things yourself explicitly is very, very painful.
Yeah, so that should work here.
Yeah.
Yeah, I think so.
As long as the construction data can be cast. Like all the construction data is just, we need to be careful that the construction data is always simpler.
Yes. If it's not, then you're not really doing the job.
Well, I'm just saying,
Yeah.
it's listed in documentation for construction.
Yes.
So suppose you have some ring or whatever, some object that is, say, let's go with black box. Say it's very hard to, I don't know, it's very complicated. And then you have join X, and then you have join Y, and then you have the same black box object, and then you have join Y. So is this algorithm going to figure out that you can actually this without going into the black box, or do you have to? Because the way you presented here, it looked like you were going all the way up to the simplest thing and then going down. But then you say that you start from the bottom, huh?
They go all the way to the point that they match.
So where there isn't.
Oh, and the
Up to
idea
the
is
point that
this
they
Y
match.
should bind to this Y rather than the outside. Because these rings should be able to be compatible. You shouldn't have joined this Y and suddenly.
Okay, so consider this, considering the data specifying what you're talking about, consider two polynomial rings QXY and QXY indeed with different different term orderings, and suppose you've constructed the quotients of these things by an ideal. And you've used exactly the same ideal on both sides. You might think it's a good idea to reformat that data into a Grosvenor basis of the ideal. But since these two rings now have different term orderings, that might not be a good idea.
Yeah, I think you really need, for multivariate polynomials, you need to take the term ordering into account.
Yeah. And the term ordering
But that means that means that it becomes impossible to see how
no. So what you do
polynomial rings are not isomorphic if their term ordering doesn't.
Either there's
then it goes wrong.
Either there's an order on term orderings in which this term ordering takes preference over this, or term orderings are incompatible.
No, here's another one. You do, like, we have two ways to match them up. We have the way that they're added, and that's the way that they're called. Yeah. We have the ordering on the term orderings. They both have to satisfy the property of being able to merge.
Yeah.
You have to check those.
Yeah, the term ordering is extra data that might be compatible.
No, what I'm saying is that the construction functor for multivariate polynomials
would have data which is term order.
Yeah.
Yes.
I mean, there are some cases where you could construct something canonical if you have different term orderings. Like, you know, one is lexical vertical term ordering and backward flags, and you know, you have X, Y as backward flags, and then Y, Z, and this is flags, and then you can construct a block model. You cannot, if you intermix variables, like your T example earlier, I don't think you can do it. I'm not sure. But
well, the thing to do is that term ordering information would get passed. It would get, when you ask for the construction, it would be returned. And then when you wanted to construct it, it would be returned back to whoever wrote the multivariate polynomials.
Here, for instance, if you take this,
these are different.
If you take this ring, Ri, I mean, in both cases you're taking the same quotient, but for R1 you take X to be bigger than Y, and for R2 you take Y to be bigger than X.
But then one is Q adjoint X, Y, and the other is Q adjoint Y, X.
No. They're constructed this way. You've just prescribed another term ordering.
Term ordering is different from the ordering of the variables.
Yeah.
So according to the coercion system, there should be a map between these things. But if you represent your ideals now with respect to a Grosvenor basis, then these two ideals would have syntactically different bases because it's different term ordering.
So what would happen is if one of these term orderings was preferable, like you could either say, when I realize that the term ordering is different, then you just give up. That's one way to do it. The other way to do it is say, if there's different term orderings, we have a preferable, we have the term ordering that we prefer. Like there's an ordering on term orders.
No, the thing I was actually thinking was that for the system now, it becomes very hard to even decide whether the structures have been compatibly generated.
Oh, because it has to, yeah.
Well, I mean, you definitely don't want to go in and test whether the ideals are equal, because that's an expensive test. So that should never be done by the coercion system.
Well, then it just
but if
fails.
those,
That's all right. It just fails then because it's a computationally hard thing. I don't see the point with that.
Yeah, I would say it should
yeah,
just
but
fail.
that throws out. But then you basically throw out any coercion between quotient objects.
Multivariate.
Why?
Because then it will always, by that argument, it can be expensive to test whether ideals are expensive. So it should never whether ideals are equal. So it should never test whether they are. However, if they're given identically with the same generators, then it would actually be cheap because that's a syntactic thing to check. But
Well,
then you really have to keep the basis for the ideal as given by the user at point of construction, and not replace it by a Grosvenor basis.
Yeah.
Well, you can, I mean, you can keep the basis, I mean, you can do both, right? You can replace it with a Grosvenor basis for the purpose of doing computations and keep user basis variable.
Yeah. So, but
Well,
this sort of seems to be an argument that it's even more important to keep the user basis.
There's a similar example with number fields where you describe the number field in some way and it might use a different representation underneath. Isn't that sort of similar?
Yeah,
yeah.
Very similar.
Yeah. So that's one of the consequences.
But if whenever you do something like that, where you're saying the user, I can optimize the object the user gave me, you're going to have to be able to translate back and forth between what the user gave you and this optimized object, which means that the coercion model can ignore the fact that you optimized it.
Yeah.
Just pretend you didn't.
Yeah.
Even for number fields, it's expensive, isn't it?
Yeah, but
it's like matrix arithmetic.
I mean, to do arithmetic in that portion, you have to compute the
but
anyway.
if you're going to do that,
you have to solve ideal numbers.
Yeah.
So I mean, I think you could just test. I mean, you're adding two of those things, you run into the risk actually computing Grosvenor basis.
Yeah, no, that's for automatic coercions, that's really not acceptable.
Well, but I mean, you have to do arithmetic in that object. You have to do it anyway. I mean, this quotient ring is no good if you not compute the Grosvenor basis, because you can't work with the elements.
Yeah.
Yeah. I mean, the fact that arithmetic in the ring might be expensive, I don't think is an argument to make stupid data manipulation expensive with these objects.
But hang on, I don't understand why, because elements are represented differently. If I cast something from R1 to R2 explicitly, doesn't that imply it has to convert from one form to another? Isn't that already hard work? Sorry, I'm not sure. This R1 or R2 being represented with
So I take one polynomial from R1 and one polynomial from R2 and I try to add them.
No, but I even mean if you take an element of R1 and you explicitly coerce it to R2, should that be an expensive operation anyway?
No, that's just mapping x, y to x, y.
But don't you choose
if the Grosvenor bases are different?
If the Grosvenor bases are different, don't you actually have to do some work?
No, that's only, I mean, it might be an object in which it's difficult to check equality. That's no problem. You just don't.
Okay, well, I just don't understand Grosvenor bases well enough, I think.
I mean,
don't you have
objects in there would simply be the cosets of that ideal. That those cosets are given by perhaps not canonical representatives.
Right,
it's not really an issue.
Right. But if you only ever store the canonical representative, then it might involve computing the canonical representative for this.
Right. Yeah. You probably don't want to do it.
That's fine. But which ring, like, if you try adding something in R1 and R2, where does it land?
Well, that's.
I mean, it depends on whether or not these are compatible or which one is better.
So do you actually want to make those two things compatible?
Well, that's the question, are they? But I mean, The thing is, it's not an individual question in this case because we're fitting it in a larger scheme.
So, but
The question is basically, can quotient operations be fitted in this scheme?
yeah,
Well,
at
if
which
it
point
weren't
in the
term
chain
sure,
of functors, at which point are you setting the order of the terms? Before the quotient. So you should say that setting an order is a functor that is.
No, not setting an order is a.
Because we
a join is a variable with the extra data about joining y is term order.
Yeah, you can't set the order of you can't set the term order after you create a ring. I don't think. You have to specify a ring creation.
Well, but you just think about it as you're joining x, y, and then you set the order, and then sort of setting a different order just blocks the coercion to.
So but that breaks the entire variable thing because it is important for the whole model that variable adjunction goes one by one.
Yeah.
No, that's fine.
Yes.
So term ordering should, if we're using that model, we cannot do anything we cannot let things decide by whether term ordering is right or not.
Term ordering would be something that is attached to the last variable you adjoin.
Yeah. Or maybe to each variable you adjoin, you attach the term ordering.
And so when you have q adjoin x and you say I want to attach y, make it a multivariate polynomial with this term order. And then on the other ring you have I want to attach y and make it a multivariable with this other term ordering.
So you adjoin y as a multivariate variable with this order with respect to the previous variables, and that's it.
Yeah, that's all you need to do.
And then when you try to check compatibility, you check that all the variables that appear in both are compatible, and that's it.
Yeah.
The ordering is compatible because maybe you have some variables before that appear in one of the things,
Right,
and
which
not in the
means
other
this
one.
would not work because the orderings are not compatible.
Yeah.
You would not be able to coerce that.
But they are
Right, so these
different
examples,
things.
because you had examples where variables got spliced in the middle.
Yeah.
That now is a problem. Yeah. Because the term ordering there is not.
So what the thing is, I would say, you could say, well, both of them have lexicographic term ordering.
Because.
Yeah.
Because that's the ordering by
Exactly.
default.
So if his example had a splice where it was in the middle both lexicographically and where you put it, then it would work.
Yeah.
So when are these two compatible then?
Never.
If it's lexicographic term ordering.
Yeah. And Q joined Y joined X will be compatible if it's reflex.
No reflex. Something else.
Yeah.
Yeah.
No, I would say
This
it's not compatible.
Yeah.
No, Q join Y and join X is not compatible.
It should not be.
Because you're joining the variables in the opposite order.
Okay, sure.
Yeah.
You're going to join a variable that lands in a different.
Does it make any sense to do this? Screw around like this with different term orderings?
I would say if the term orderings don't match, just throw an error.
It's more like a question because we can, right? I mean,
How often are you working with rings with different term orderings but the same variable names?
And you want to go from one to the other.
And you want to add things.
Yeah, you want to
Yeah.
mush the elements
First
together.
do something
And how
with
do you know
respect
which
to
order
graph
you
lex
want?
and then walk to lex or
The sum.
And generally, when you do that, you want the letters to match up, and you want to ignore the fact that the terms differ.
Is it confusing enough to write down? We would never be able to do it.
assuming that's the whole that's the whole idea of giving variable names.
So what should happen is this should not work in coercion, it should work in casting. Or forcing.
Shoving through a very small.
Okay, so kind of to move on a little bit, I would say try it out, see if you can break it. I'm very curious if you can come up with an example that's not transitive.
Yeah.
That would be really cool.
Not associative.
Associative.
Yeah.
Yeah. And then, so kind of to move on a little bit, because there's some other questions I want to ask. So the implementation in Sage, these are the requirements. We need it to be fast. We need it to be non-intrusive, meaning we don't want to have to cast everything all over the place. The reason we have this is so that things work naturally. We want transitivity.
What does that mean?
When you swap it, different orders.
A plus B equals B plus A.
Yes, A plus B equals B plus A.
Or at least
That's commutativity.
I would call it commutativity. Oh, that is
Yes.
commutativity.
Yeah.
That is.
Is that what you meant?
That's what I meant.
Whoa.
Yes, that's what I meant. Oh, no.
No, but
No,
also
we want it to be
yeah.
transitive. We want the diagram to be transitive.
Yeah.
We do want commutativity, but we want the entire diagram to be transitive.
What
Yes.
does that mean?
That's what I was meaning when I read.
Transitive closure of the graph.
Yeah, if you do two of them end to end somehow, you should.
Yeah, if you can go from A to B and you can go from B to C, you should be able to go from A to C.
Just of the coercions.
Of the coercions. Yes.
Oh, and that should be automatic.
Yes.
Yes.
Ooh, okay, yep.
I mean, it should be.
Yeah.
It'd be really
sure
odd
this
to
is
say,
breakable.
well, as long as we put this middle thing in here, now we can go through.
Is that in preference order?
I think transitivity is a special case of associativity. When you add A plus B and then you add C, which is down here, it should be the same as if you added A plus C and then went down like that.
No, you mean B plus C.
B plus C.
No, I don't think it is.
Draw the dagger.
Yeah, okay. So we have.
I mean, transitivity doesn't even make sense in favor of associativity, right?
This is what the problem could be like. If you end up here, if you do it in one order, here, if you do it in the other. And that doesn't violate transitivity of the diagram unless, well, when you add these two elements, it shouldn't matter which way you came from. But these two things not being the same thing is bad.
Yeah.
Yeah.
That's associativity right there.
Yeah. And transitivity is what?
Transitivity is the fact that if you then get all the way down to here, that they
So I was wrong. So you could be transitive without being associative by having the two things that are the different answers to the associative question coercing down to the same thing.
Yes. I can't think of a way you could do that, but
I'll figure out it's possible.
yeah.
So transitivity is still a statement about three objects?
No, associativity is a statement
So
about-
can you draw a transitivity on another picture?
So this is transitive. So, like that. So you do, well, assuming you have associativity, then transitivity would mean if you do C plus A and then plus B, you get that. Well, let me think about,
I thought transitivity meant if I have an X
If it
and
works.
A, and
Yeah.
I
I don't think it
do
can be.
C of B of X, that's the same thing that I get as if I do C of X.
yeah.
Right, that's transitivity.
But
Yeah, so
there's
I do
C.
like-
But C there is a coercion map, not an object being added. It's a different.
Can I give an example?
Yeah.
And
Yeah, it's a different thing.
Yeah, okay.
so the example is on the left side you adjoin X and then you adjoin Y.
Like this?
Struggling with language here. This is
Yes.
struggling.
On the right side you adjoin X and then you adjoin
Let
Z.
me tell me if this makes sense.
And that's clearly not compatible.
No, it's not.
I have A.
But in the middle you adjoin X, comma Y. You adjoin X, then Y, then Z. And X, then Y, then Z is compatible with either one.
Yes.
Or it could just use.
So you're saying if
This is
you,
nothing,
like
but
A,
this has nothing to do with automatically. I mean,
And then you have
the
C and Q
sensitivity,
adjoin
the objects that the parents
X, Y,
Why
Z.
is it
there
interesting?
do not
And now
exist
you
before. You've not
have
created any new parents.
A plus B equals C.
yeah. Okay, so here's where it fails.
So that fails
A plus B
transitivity.
fails, but A plus C plus B
Well, no,
succeeds.
A plus B plus C fails if you do it A plus B
plus C. It succeeds if you do it A plus B plus C.
Yeah.
So
Okay.
it fails both.
But that's actually the most graceful failing that you can have, because at least you don't get different answers. One way you do get an answer, the other way you don't.
Yeah, that's a.
Yeah.
I don't think you
Wait,
you
this
expect to
this
have
failing
different.
is the issue
Yeah,
of
so that- I
multivariate
think this is still
polynomials
acceptable.
versus
No, it does A plus
non-linear.
B, it doesn't, these are incompatible. A and B are incompatible. Because it doesn't know which comes first, the Y or the Z.
Oh, right, it doesn't know which comes first, it just says chuck it, because I can't do it.
Yeah,
So
So-
Z of X plus Z of Y.
The C basically tells it which one's first.
yeah.
Yeah.
So associativity is a statement involving new parents that didn't exist when you started.
Uh-huh.
But transitivity, what Craig is calling
Yeah,
transitivity,
Yeah.
is just a statement about.
Yeah.
All the
Guys,
parents
you
that
can-
exist. Yes.
Okay, great. Okay.
Yeah.
Okay, so